Welcome to our lesson on functions. What the heck is a function? Well, this kind of gives you a nice clue. It says converting inputs to outputs in a most reliable way. In some sense, they're like machines. Just thinking abstractly, they're like machines. Machines that work. I invite you to think of, for example, an FM radio that works. So, what do you expect? You expect that if you set your dial to 92.5 FM, you will hear KQRS. And if you set your dial to 107.9, you will hear Cool 108. And of course, there's lots of other choices. But what makes this a function, what makes this FM radio behave like a nice function, is that if I now go back and reset the dial to 92.5, I'm going to get KQRS again. And if I reset the dial to 107.9, I'm going to get Cool 108 again. It's very predictable. It's very well behaved. It's very nice. You got to like a radio like that. Okay? Most radios are like that. So that's the good news. Now, of course, you could do something like this. You could set it to 105.1, and then you're going to get this station that is called Love 105. Who knew that they had a radio station like that? But they do. They have a radio station called Love 105. And if you set your dial to 105.3, you're going to get Love 105. And if you set your dial to 105.7, you're going to get Love 105. Now, this is okay. It's still a function. The radio still works, right? Your radio's not broken. It works just fine. If I set it to 105.1, I will get this answer. And if I set it back to 92.5, I will get this answer. And if I come back to 105.1, I'll get this answer. And if I come over to here, I'll get this answer. And if I go back to 105.1, I'll get this answer. And if I come back to, I get this answer. That's okay that more than, you can set your dial to these 3 different places and they all give you the same output, so to speak. You know what? That's a good place for me to start putting the words input and output around on them, trying to erase all this green. Look what I did. Look what I did. Too much green. Whoa, see, I took a V out. Okay. It's supposed to be a blue V. Okay, let's get this right. So anyway, I'm gonna throw some words around here. You might have thought of this as the input, and this is the output. When you set the dial, it's kind of like you're setting the input. I set the input to 92.5, and this input is converted to an output in a most reliable way. I always get KQRS. Okay, that's the idea. And it's okay. It's okay to have different different inputs giving you the same outputs. That's okay. But I'll tell you what's not okay. It's not okay if let's just say if any input gives you more than one output. That would be bad. What does that mean in radio speak? That would be like saying, I set my dial to 107.9 and right now I'm getting Cool 108. But the next time I set it to 107.9, I'm going to get KQRS. That's not good. That's a broken radio. You don't want your radio to do that. You would not say that that radio was functioning properly. I don't know if that's why they call it a function, but anyway, you would not say that your radio is functioning properly, okay? So you do not want this to happen. You do not want to set the dial to something and get more than one answer. You always want to get the same answer every dang day. It's always Cool 108. Again, this is okay. I got different places to set my dial that give me the same answer. That's fine. As long as 105.1 always gives me this, I'm happy. As long as 107.9 always gives me this. As long as 92.5 always gives me this. So it's this sort of a one-way test or whatever you want to call it. So that's inputs, that's outputs, and I'm going to throw another word out here while we're here. Sometimes people would take this list of inputs here and they'd say, hey, we got to use a variable. Yeah, okay, call it X, whatever you want. They call it an independent variable. The dial, where you set your dial, is called an independent variable, and you can imagine why. It's because that's where you have the power. You can turn the knob and set the independent variable to whichever number you want over here, and then what comes out, of course, depends on where you set your dial, and so we call this the dependent variable. So I'm getting some good lingo out here. Got to have some lingo, right? So we got the input and the output. We got the independent variable, the dependent variable, and again, this is what makes it a function. So I've been talking here quite a lot about what makes a function, or what's the idea of a function. So I guess I'm gonna actually just put it here. I'll just say it again, but I'm gonna write it out and be all official about it. So the idea of a function is you have a sort of, that's a good definition, right? A sort of input-output device. And again, I'm speaking abstractly here. It could be any kind of device. It could be a guy sitting in a box that you pass him something, he passes you something back, whatever. Some sort of input-output device, mechanism, whatever, where a given input, whatever you hand into the box, so to speak, always produces the same output. It always produces the same output with one output per input. We might want to add that. You only get one radio station when you set the dial there. You're not supposed to get two at the same time, or get a different one today and tomorrow or whatever, with one output per input. Okay, programming note. I'm done talking in the abstract for now. So it is important to realize function is sort of it's a general idea. It doesn't always involve, people are used to, it's like, hey, it's algebra. Shouldn't we have like equations or something? Shouldn't we be making graphs or something? And it's like, well, yeah, we're going to be doing that. So, but I want to write this. Not programming note. I just want to call this out explicitly. Even though the concept of a function does not require us to think in terms of like equations and graphs, I guess you might say. That's what we're going to do for the rest of the course. We're going to do that anyway. We will be doing this for the rest of the course. But don't lose sight of the idea that a function is a general concept. Now, what we're usually going to do is we're going to use equations to represent our relationships. So instead of having relationships that are like, there's a guy in the box or whatever that turns an input into an output, we'll use equations to turn our inputs into outputs. So here's some equations, and we were just graphing things, right? So I wonder if you can look at these two equations, and I wonder how fast it would take you to make graphs of these things. It'd be a great exercise if you paused here and graphed those things. And if you didn't, then here's what I'll do. I'll graph them for you. This won't take long. If I want to get y by itself on this one here, so I'm going to basically add 2y to both sides. I've got x squared equals 2y. So if I divide both sides by 2, I get half x squared equals y, which I'll also switch the sides around while I'm at it. This is what I'm really graphing. It's easier to solve the equation for y, get an explicit solution for y, and then just start plugging into it. Now usually we make an xy table. I'm not going to write the xy table. I'm just going to speak the xy table. If I plug in x equals 0, 0 squared is 0, half of 0 is 0, y is 0. So when x is 0, y is 0. Okay, let's plug in, I don't know, I'm going to plug in a 1. If I plug in 1, 1 squared is 1, times a half is a half. So when I plug in 1, I'm at a half. Fun, right? And then if I plug in x equals 2, 2 squared is 4, but half of that is 2. So when x is 2, y is 2. And maybe we'll go one more in this direction. I'll plug in x equals 3. 3 squared is 9. Half of 9 is 4.5. So when x is 3, I'm coming up here to about 4.5. And by the way, you know that if I plugged in a negative 3, I'm going to get the same thing, because when you square the negative 3, it becomes a positive 9, and half of that is 4.5. And so basically over here at negative 3, we also have that, and all of these points, really. You can just sort of make little reflections. We got a nice parabola. Yep, that's a parabola. Nice parabola. Cool, right? All right. What about this one over here? Well, with this one, if you wanted to get y by itself, you'd have to first get y squared by itself, 25 minus x squared, right? Then you'd have to take the square root of both sides, which is plus or minus. Don't forget that. And you've got this. So we're graphing that. Now I'm going to do the xy table, but again, I'm not going to write it. I'm just going to speak it. If I plug in a 0, what happens? I got 25 minus 0 is 25. Square root of 25 is 5. Y is plus or minus. Don't forget the plus or minus. Plus or minus 5. So when x is 0, I come up to 5, but I also go down to, let's make sure I go to the right spot. Yep, negative 5. So I got 2 points for the price of 1, so to speak. I'm going to plug in, hey you, I'm going to plug in something else. I'm going to plug in, you know what I'm going to do? I'm going to do this trick. Remember this trick? Plugging in x equals 0 gives you y-intercepts. If I plug in y equals 0, and I can kind of do that. If I plug in y equals 0, what's x? Well, looking over here, I'd have to have a 0 in the parentheses too, or in parentheses, in the square root symbol too. That would have to be a, hey you, come on. This would have to be a 0. So what's the x? The x has to be a 5, right? Because 5 squared is 25, and then when you subtract from 25, it's 0. So plus or minus 5 will both work. I should put that here, really. Whether I used a plus 5 or a negative 5, I'm going to square it. It's going to become a 25. So anyway, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Of course, you also could have, if you wanted it to make it a little easier on your eyes, you could have just rearranged the equation for x or whatever. But let me go back and start plugging in values for x again. If I plug in a 3, 3 squared is 9. 25 minus 9 is 16. Square root of 16 is 4. I got plus or minus 4. So when x is 3, I go up to plus or minus 4. And by the way, if I used a negative 3, I'd get the same thing because I'm just squaring it. So again, it's 25 minus 9, which is 16, which is blah, 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 blah. So I'm up to here. And hopefully you remember this one from last time. We're getting a nice circle. This comes out to a nice circle, and you can plug in more points if you want to define it even better. So that's just a reminder of how we turn equations into graphs. Now, what's all this stuff about functions? This is a function. Yes, it is. What was it that makes it a function? It's a sort of input-output device where a certain input gives you the same output, one input per output, okay? What's the input? Well, you want to think in terms of almost like having a slider along the x-axis that sets your input. If you kind of have this image in your mind, it's like, okay, I'm going to set the input to 3. Woo, I get this value for y. I'm going to set the input to 2. Woo, now I get this input. Let's set the slider over here to -2. Now I get this. Can you see how well behaved this is? Everywhere you set the slider, you're getting one nicely defined value for your output. And of course, if you put the slider back to the same spot, you'll get the same y value again. And yeah, that works. That works. Notice how it does not work so well over here. If I set the slider here, well, wait a minute now. I'm getting 2 different outputs. That's not what we want. We want one output. So this is not a function. So going by our very wordy kind of definition up here, if I set my input here, I get 2 different outputs. That's no good. I'm supposed to get 1 output per input. That's no good. Of course, what people usually do is they say, you know what? Get to the bottom line here. Notice you can slice it and you'll hit the graph in more than one place. That's called a vertical line test, and I'll write it out this way. If any vertical line, if you can find any vertical line anywhere, but it's got to be vertical. If any vertical line can be found that intersects the graph more than once. And that's important, more than once. Once is fine. It doesn't even have to intersect the graph. It could intersect the graph not at all. That's fine. You know, functions don't have to live everywhere. Some functions only go from like here to here or something. Hey, there's a vertical line. It doesn't cross the graph anywhere. Fine, you're fine. But this one we're not fine, because I found a vertical line that is crossing the graph twice. That's no good. So if any vertical line can be found that intersects the graph more than once. So got to use your words very carefully here. More than once. Doesn't say it has to cross it anywhere. Just if it ever does cross it more than once, the same vertical line, then it's not a function. The graph does not depict a function. We say it failed the vertical line test. Failed the, and I usually write VLT for vertical line test. It failed the vertical line test, okay? So page 1 is basically just getting the basic idea across. What's a function? Well, it's got this special property where you set the input dial somewhere and you're going to get a known, reliable one value of output, and it's the same every day, and you never get more than one outputs, and blah, 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 blah. You can tell a graph shows a function if it passes the vertical line test. Bada boom, bada boom. Okay, now that we got this idea of a function, I want to contrast the old ways versus the new ways. Now, you notice I've got the same graph here twice. Right? I mean, these look like the same graph. On the left here, well, let's see, usually we label that as like the x-axis, we label that as the y-axis. I got this nice purple line here, and notice the arrows showing that it does continue forever in both directions. Whoops, put my y back. Okay. The old way of saying things, like even in just our last homework, is we would say this graph right there, this graph maps out all the solutions. Remember this concept? All the solutions to the equation, and it turns out the equation being graphed here is y equals 3/2 x minus 3. That's how we would have said it before. Yeah, we would have labeled this x, we would have labeled this y axis, right? This graph maps out all the solutions to the equation. You know, there's nothing wrong with anything there. But it's not new. Now we have the new ways of saying things. First of all, we're still going to call that the x-axis. But the new thing we're going to say is we're going to say this graph maps out and it's important to get a hold of the lingo. You want to get used to the lingo. So that's why I'm taking care to do this. This graph maps out all the output of the function f. F is just the name of the function. It's not a very imaginative name, but it's a name. You can call it anything. Call it ABC, whatever you want to call it. You can call it Jeff, whatever. This graph maps out all the output of the function f, which is defined by, and you might expect me to write the equation again, and I sort of will, but we write it this way now. Boom, boom, boom. There's that 3/2 x minus 3. You need that, because that tells you how to turn an x coordinate into a y coordinate, right? Except we're not calling these y coordinates anymore, except when we're speaking loosely. This is the outputs. We're labeling that x as f of x, not y, f of x. So if you compare this side of the equation, and if you compare the way we're labeling our axes, you might understand why I often catch myself saying that f of x is like a glorified version, is like a glorified y. So where we used to put a y, we're now going to put this funny thing called f of x, right? But we don't want to just put it there like it's funny and ignore it. We want to get used to this thing. What is this thing? So let me give you some stuff. Again, f. This is the name of the function. F is the name of the function. We'll have other functions, g, h, z, v, p, whatever. F is the name of the function. Okay. Now this part here, this is a little different. This part here, this tells us we're using x to stand for our input. We're using x, to stand for our input. Where are we doing it? We're doing it over here, right? This is like the rule. Hey. This is like the rule, so to speak. The formula, whatever you want to call it. You know, formula is not a bad idea. But I'm stuck. I'm going to call it the rule. The rule that basically tells us how you get your output from the input. That tells you how to determine the output for any given input. And you can see it's just an equation, right? When you're making an XY table, you would have done something like, hey, I'm going to plug in x equals 2. And if you plugged in x equals 2 here, notice the 2's would have canceled. You would have got a 3. Actually, you would have got a 0. It's just that before we would have called it an XY table, but now we're calling it an XF of x table. See, f of x is like a glorified y in that sense. So these are our basic parts. Let's see if I can get rid of that purple line. Hey, I did. These are the basic parts. And by the way, let's put a big PS over here. Let's use a pen to do that. PS. This thing is pronounced the way you say it. You say f of x. Again, x is standing for the input. F is the name of the function. F of x means f is a function that uses x as its input. And it's important to realize this is a special notation. A new special notation. That does not mean if you're driving too fast, driving too fast past this sign, you might say, hey, I think that says f times x, right? Isn't that what a parentheses is supposed to do? It's supposed to tell you to multiply stuff, blah, blah, blah. Well, no, not in this case. It's a notation. It's a special notation. A new special notation, it does not mean f times x, it means f of x. F of x. So the way I would pronounce this whole thing is f of x is 3/2 x minus 3. Okay. As a PPS, postscript, let's say I did something like this. That is pronounced f of 2 equals 0. Okay. What basically just happened is we said, hey, I want the x here because it says f of x, right? I want the x to be a 2. So you would come over to this formula and you would plug in a 2. And when you plug in a 2, you're going to end up getting 0. And that's what we say here. And so f of 2 is 0, or f of 2 equals 0. And the other thing it tells us is that we have a point. When x is 2, y is 0, speaking loosely. 2 comma 0 is a point. The point is on the graph of the function. You can graph functions, right? So we got this new notation. And then, you know what? I'm going to put a PPPS. Maybe I'll change colors here. This function language, if you will, it gets to be, once you get used to it, it gets to be kind of powerful. So try to come up with an example of what makes this language powerful. So like maybe someone comes up to you and they say, hey, you know what? Revenue is a function of price. That's supposed to say revenue is a function of price. Well, if you chew on the words a little bit, that's actually saying quite a bit. Now, loosely it'd say, oh, you mean revenue depends on price? Yeah, it does, but it's saying a little bit more than that. It's saying, means that there's like this relationship in the background, there's this deterministic relationship. Let's put it this way. There's this deterministic relationship. Not that it just depends on price, not that it's correlated with price, not that it's, got something to do with it, but that there's this deterministic relationship where if you actually specify the price, if you give me the price, if you specify a price, that tells you exactly what the revenue is. That's what a function is. You tell me the price, I will tell you the revenue. That's what a function means. It tells you exactly what the revenue will be. So if somebody uses that kind of lingo, and especially if they're a scientist or engineer or something, they mean a lot when they say that. It's a function of means a lot. I would kind of picture this in my mind. Revenue depends on price as a function, probably something like this. I don't know what it looks like really, but it's probably something like this where there's a certain price where there's usually a certain happy price where you make the most money. Just take an economic class. They'll talk about that for a week. You don't want to charge too much because then nobody will buy it. So your revenue will be zero, stuff like that. So it probably looks something like that. But anyway, just the point. Revenue as a function of price means something. Notice the of price, the of, I shouldn't scribble all over what I'm writing, but the of, let's use a different color. Of points at your independent variable, which is usually what we graph along the x-axis, right? So that's why I put the price on the x-axis. That was my independent variable. I knew that because it said of price. It's a function of price. You're setting the input slider along the price axis. The function is of price. You tell me the price, I'll tell you the revenue. Boink, boink, boink. Okay, cool. Well, now that we got this function notation, we're going to need to work with it. So here's some function notation right here. Here's some function notation right here. Okay, let's work with it. Practice with our function notation a little bit. We need to be able to read it, write it, know what it says. So I'm given a function here, which I'm not giving you the equation, I'm just giving you the graph. Now, usually that's even better than having the equation. I guess I shouldn't say usually, but often that's better than having the equation. I love having a graph. You can see exactly what's going on here. Plus, it'd be kind of hard to write the equation for that. It'd have to have like 3 pieces to it. This line, this line, this line. Anywho, I digress. I digress without an eraser. Come on, eraser. Okay. Let's see. If that's the function, this is my x-axis, this is my f of x being plotted here. It says here, evaluate f of 0. Okay, what does that mean? Remember, what's in parentheses stands for your input, which is usually what we use x to stand for our input. It says x should be 0. So when x is 0, I'm here. That's where I'm setting my little input dial, so to speak, my slider. You read off, where's the function? It's down here at -2. So f of 0 equals -2. And that's how you play this game. What does this say? Solve f of x equals 0. How come it doesn't say evaluate? It doesn't say evaluate because over here, evaluate is where you know what x is, you go looking up y. Here, we don't know what x is. That's our question. What the heck is x? So in some sense, you're like solving. Hey, what the heck is the x here? What's the x here? What I know is that I should get 0 sort of from my y coordinate, speaking loosely. But 0 is the output of the function. So you look on the graph and you say, well, there's where I get an output of 0. And actually, you know what? Over there. So I got 2 solutions, really. I got 2 solutions. So the solutions are x equals, looks like that's a -2, and it looks like over there that's close enough. I'll call it should I call it a 3? I'm going to call it a 2.9. Somewhere around there. Okay, so again, it's like that's the x, that's the y. Speaking roughly, that's the x, that's the y. So f of x equals y. F of x is like a glorified y. just as a quick way of making sense out of it. Might as well leave those there, right? Let's look at this. Whoa, that's a little bit bigger. But you just kind of pick it apart. You say, well, this says 2, and it looks like I'm supposed to multiply by this thing. Remember the f blah blah, that's a notation. That does not mean multiply. That means go figure it out. F of 1, I got to go figure out my f of 1. So I come over here to my graph. Maybe I erase some of this stuff. And I say, okay, f of 1 means set x equal to 1. Set my slider equal to 1, and then look up the y value. It's a -2. So that's what that is. And then I'll come over here. I'm supposed to be subtracting, but I won't do that yet. First I have to figure out what this is. What's f of -3? So I come over here to x, set my slider to -3 here. And I look up the y coordinate, and it's a 1. So this is a 1. So what I got? I got this 2 has to multiply this -2 minus, and that's a 1. So that's a -4 minus 1. You're getting a -5. Kind of get the idea here? It's almost, in some sense, it's almost like, you know, I was going to say it's like having parentheses almost. Go figure out what f of 1 is. Go figure out what f of -3 is. Then you can try to figure out what the whole thing is, right? Kind of do those things first. This is a similar set of exercises. What's different here is we're not given the graph of the equation. We're given, or the graph of the function. We're given the formula for the function. We're given this relationship here, x squared minus x. F of x is x squared minus x. We could graph it if we wanted to, but I don't want to. So this is saying f of -2. Again, remember, that means set your x to -2. So let's set my x to -2. Remember, when you plug in, you use parentheses. You've heard me say that numerous times. So I have a -2 in parentheses, that gets squared, minus another -2 in parentheses. A -2 in parentheses, you square it, it's a 4, and then here you distribute, -2 is +2, and so we're getting 6. F of -2 is 6. We would have the point -2 comma 6 if you made a graph. When you plug in -2, y is 6. Okay, I want to go down and do this one next. F of -x. You might say, what's that telling me to do? Or you might ask. It's all it's asking you to do is to plug in -x. You must be wondering, why would I ever want to do that? Trust me, that's setting us up for something that's coming a little bit later, something called transformations of functions. But for now, what I want you to do is just kind of, what I want to say, go with it. What's in the parentheses gets plugged in. I got a -x in my parentheses. That gets plugged in. Gets plugged in where? For these x's. So I come back up to my equation here. I erase the blue thing because it's, I erase the blue thing. Okay. And I go like this. I say, okay, f of -x would be, I see an x. Plug in a -x squared. Minus, I see an x. Plug in a -x. Using parentheses. Now here, this is like a -1 times x, so that squares to a +1, x squared. And then here you get a plus x. X squared plus x. So that's kind of interesting. F of x is x squared minus x. F of -x is x squared plus x. What's this one? This one's asking us to do, this is different. The negative's in a different spot. It's not the same as this one. Up here it said plug in a -x. That's not what this says. If anything, this says don't plug anything in. It just says plug in x, which that's already been done, really. It just says actually take f of x. Take f of x as is, might be the way to say it, and then put a negative in front of that. In other words, -1 times the function. That's what we're doing. This is a -1 times the function. So I go -1, and then I write my function down. My function is this, x squared minus x. And so what are we getting? We're getting, well, if I distribute, we're getting -x squared plus x. So notice these two things are not the same. Right? It depends an awful lot where the negative is. Is the negative being plugged in, or is the negative out front? Makes all the difference in the world. Okay, 2 more of these things. Let's go back to blue for a while. Oh, here's another one of those solve things. So the main point here is that we're not plugging in x. We're setting the function equal to 12. Different game, right? Set the function equal to 12 and solve for x. So here's the function, set it equal to 12, and now we have to solve. What the heck is x? So we've had some practice with this kind of stuff, right? We can solve this by factoring. You make the right side equal to a 0. You factor the left side. Hopefully you're recognizing a rather friendly trinomial there. Factors of negative 12 that give you a negative 1 are negative 4 and 3. Bada boom, bada bing. You look at this part and you say, oh, so x could be, looking here, a negative 3, or x could be, looking here, a positive 4. So if we were to graph this thing, there would be a point, x is negative 3, y is 12. You would also find a point, x is 4, y is 12. Whatever it looks like this. So if you were to graph that function, you would see these 2 points on it. Okay, and then we save the best one for last over here, of course. Look at this gobbledygook, huh? So when you first see something like this, of course it's going to look like gobbledygook. You might even be justified in calling it gobbledygook, but not when you're doing the homework, because I'm going to show you what it means. First of all, what does this mean? F of is how you would say that, right? F of m plus 2, which means I'm plugging in m plus 2 into my function. Again, that's how my function is defined. So I take the input, which is m plus 2, and I square it, and then I minus my input. And of course, whenever you plug into anything, you use parentheses. So we can sort of keep going with this, make it look a little better. If you were to FOIL this out, remember you'd have to do this kind of stuff, right? M plus 2 times m plus 2. And while I'm at it, I can distribute here, minus m minus 2. But this foiling part, I'd have to have an m squared, and I have a plus 2m, and then another plus 2m, and then a 4, and then the minus m, and then the minus 2. So this is coming out to, f of m plus 2 is coming out to an m squared plus a 3m plus a 2. And we'll just kind of have to hold on to that for a second, because that's all we've got is this part right here. Moving right along, we have to look at this other term, and this other term is a 3 times, and we should first figure out what that is. F of m minus 2. Okay. So we got to figure out what is f of m minus 2. So you can kind of see it's going to be very similar. It's just that I've got an m minus 2 squared there, and then I got an m minus 2 here. Again, I'm plugging into this formula. So you take the input squared minus the input. The input's m minus 2. So I take the m minus 2 squared minus the m minus 2. If you work this one out, let's see, I'll FOIL this right now. I'll get an m squared minus a 2m minus a 2m plus a 4. And then I'll distribute over here, minus an m plus a 2. So I'm getting that f of m minus 2 is equal to m squared minus 5m plus 6. Hold on to that result. Get a new color. Okay, so what we were originally faced with was to take f of m plus 2, which is right there. So I'm just going to take it. And then we're supposed to subtract, so I'm going to subtract 3 times my f of m minus 2, which was this part. So this part goes here. See how you just kind of piece these things together? A lot of this, advanced algebra stuff, it's all about just reading your equations very, very carefully. Your equations, your expressions, your functions, just reading very, very carefully. So just to finish this up, m squared plus 3m plus 2, I'm distributing a negative 3 here, negative 3m squared plus 15m minus 18 is in the end going to give me a negative 2m squared plus an 18m minus a 16. And if I double check, I say, yay, that's what I got before. Good. Probably on the right track here, huh? Well, now I need to shrink this stuff up so it gets out of my way. Okay, well, I hope you're grooving on this idea of a function and this function notation. I want to do one more page because, first of all, I haven't really stated carefully a formal definition. So let's do that now. Let's give a sort of a formal definition. I suppose sort of formal. It sounds like business casual or something. Anyway, a more formal definition. So let's do it. A function, underline it, that's what we're defining, is like an input-output machine. And I will put machine in quotes, even though it's a formal definition. It's like an input-output machine, which defines one specific output. One specific output. Yep. Value for each output value, I suppose I should say, for each allowable input value. Sometimes it won't take something as an input. Say, hey, I want to give you a 5. I don't want a 5. Well, you don't give it a 5 then. But anyway, one specific output value for each allowable input value. Let's make it clear. More than one input may, to speak loosely again, point at the same output. That's okay. Remember the radio station. It's okay if you set your dial to 105.1 and get one radio station, and you set it to 105.3 and you get the same radio, even if you set it to 112 or whatever. If you keep getting the same radio station for different settings, that's fine. That's fine, but it's not fine. A particular value of input should only point at one value of output. You shouldn't set the dial to something and get more than one radio station. A particular value of input points at only one value of output. Okay, and you might even put in parentheses here, the graph will pass a vertical line test. Good reminder. Sometimes the easiest way to see if you have a function is to just make a graph and say, is that passing the vertical line test? Yeah, it's a function. Sometimes the graph will pass and I'll just abbreviate it VLT for vertical line test. Cool. There's our formal definition. We can almost end. I want to end with this exercise though. Here's a bunch of equations. They all look cool. Do they all represent functions? Or actually, let's ask this question even more carefully. For each of the following, determine whether: is y a function of x? Is x a function of y? Are they both true, or is it neither? What's this stuff about x a function of y? Well, it's convention, of course. Usually when we're talking functions, we say x is the input, y is the output, but it doesn't have to be that way. What matters is the idea of if you, for y to be a function of x means for every x you plug in, you get one value of y. If x is a function of y, then every y you plug in will point at one value of x. Kind of like that. Here's how I recommend you fly on these things, actually. X plus y equals 25. Let's take this one. What I would do is I would solve explicitly for y, and then I would solve explicitly for x. And then I would just look at those two equations and ask the question. If I were to make an xy table here, I plug in an x, do I always get the same answer for y? If I keep plugging in the same value of x, will I keep getting the same value of y? Yeah, I will. Or for this one, if I keep plugging in the same value of y, will I keep getting the same value of x? Yeah, I will. So up here, no matter what x you plug in, you get the same value of y. Y is a function of x. Y is determined by x. X is independent. It tells you the y. Here, it's the opposite. You plug in a value for y, it tells you the x. X is a function of y. It worked. So the answer to this one is both. Both. What about this one? Well, I like the idea again of just solve the equation explicitly for y, solve the equation explicitly for x. So how would I do that? I would have to first subtract y on both sides. That would get me x squared, but I don't want x squared, so I'll have to take the square root of both sides. And here's the thing, you'll have to put a plus or minus in here. And so what this is showing us right away is that if I plug in a value for y, am I going to get just one answer for x? No, I've got this plus or minus in front that says I'm going to get two values most of the times. So x is not a function of y. Okay, it does work the other way. Over here, if I were to plug in a value for x, it's going to solve out to a single determined value of y, nice and predictably. So that works. And so our conclusion for this one is y is a function of x, not vice versa. Or you know what? Even better. I got an easier way to say it. I do. Okay. It's choice A. Choice A. Y is a function of x. X is not a function of y because of that plus or minus thing going on there. Now, once you're onto that trick, you'll pretty quickly catch on here. If I were to try to solve for y, I would have to first subtract the x squared from both sides. Then I would have to take the square root of both sides, and that's going to be a plus or minus. And as soon as you put that plus or minus in front, it means that when I plug in a value of x, I'm going to get two values of y. Y is not a function of x. And you can see that the same thing's going to happen if we solve for x by itself. Equation's going to be very similar, and we're going to have the same exact problem. You plug in a value for y, you're getting two different values for x. So the answer to this one is either. Or if you want, you can put D. Can you tell what this other one's going to be? If I solve for y, I'm going to have 25 minus x, but I have to do a plus or minus square root. Y is not a function of x because there's two values of y for a particular value of x. Y not function of x. Now if you solve it for x instead, all you got to do is subtract y squared from both sides. And here it does work. It does work. If you plug in, make up a number for y, I'm only going to get one answer for x. Doesn't, different values for y, different values for x. It's going to work just fine. And so this one is an example of x is a function of y. So this is choice B. A couple more, just some graphs here. Now with these, you can just be thinking vertical line test, so I'm hoping it jumps out right away. This one is not a function. Fails the vertical line test for sure. Not. Now, this one's a little more tricky perhaps. Some people don't like that. They're like, ooh, something wrong there. That can't be a function. It's screwy. Screwy things can't be functions, but all vertical lines, any vertical line crosses it, or I should say there's no vertical line that ever crosses it twice or more. I don't care if it misses. That's fine. If it misses, that's fine. So yes, this one is a function. It's fine. It's fine. Who cares if it's weird looking? It's still a function. It's just going to have that property. Now the reason I drew this one is because we're going to have a function coming up a little bit later in the course called the floor function, floor of x. And the floor of x, when you draw it properly, looks something like this. It's got a series of what we call jump discontinuities. So it's kind of like y equals 1, y equals 1, y equals 1, boom. Y equals 2, y equals 2, y equals 2, boom, y equals 3, y equals 3. And you notice you've got this open circle here. So this is kind of like saying, let's say this is x is equal to 1. This might be y equals 1. And then if you go to x equals 1.00000001, then you're just beyond this open circle. So the open circle is kind of saying you don't have a point here. The point's down here. But if you get anywhere past x equals 1, you should be up here. So it's called a jump discontinuity. Anyway, you will not draw that to represent that. A lot of online graphing, free grapher things, they can't handle these open circle solid dots, and so they'll give you a graph that looks exactly like that, like steps. But can you see how this fails the vertical line test? So you would not want to draw that and say that it was a function, because it's not a function. Vertical lines do not pass the vertical line test. Okay, so that's not a function. So if you have a vertical line anywhere, or really, if there's any vertical line that cuts it more than once, it's not a function. Okay, that felt like a pretty good workout. That's our introduction to functions, which we will be playing with for the rest of the course.